Swayam Prabha. Digital India. Educated India.
Welcome to this session on electron beam welding and plasma arc welding processes under the course Advanced Manufacturing Processes. These two are advanced welding processes being used nowadays in many applications. Let us discuss about the principles of these two processes, the requirements and their common applications, etc. in this session. Let us discuss about the electron beam process first. This electron beam process is a fusion welding process in which coalescence is produced by heating and consequently melting the workpiece due to impingement of the concentrated electron beam of high kinetic energy on the workpiece. As we have already discussed while discussing the electron beam machining process, the principle is almost similar, in which we have discussed like this. In electron beam machining also, the basic requirement is the electron beam. Now, how we manipulate this electron beam, how we use this electron beam to work the workpieces or to cause effects on the workpieces, this is the technology we will be varying in case of electron beam machining, in case of electron beam welding. So, basic process remains same. So, there will be one electrode. So, or this is, say we can say this is a cathode, we can say this is a cathode which will produce some electron beams or electrodes, and they will be attracted towards an anode system, and this electron beam will be ultimately focused to a particular spot where the workpiece will be placed. So, there will be a focusing mechanism on the way, as we have also discussed regarding this. So, there will be a focusing, this will be beam focusing mechanism, focusing device, and this will be the workpiece. This is the electron beam coming out from the cathode, and this is nothing but the anode. This is the electron beam. Now, in case of electron beam machining, we have found that this is upon hitting by this electron beam on the workpiece. So, this portion gets heated up, and consequently this heated portion gets melted and evaporated out. Now, the same principle can be slightly modified if we place two components here having the interface at this point, then this material and this material both interface having at this point and the beam is focused at the interface. Now, as in the case of electron beam machining, so this interface of the two materials to be joined are heated, interfaces are heated up by the application of this incoming electron beam. Because of this heating up of the surfaces, they will melt and they will get fused upon cooling. So, this is the basic principle involved in electron beam welding process as well. Now, let us look into different aspects and the process parameters, that is basically the conditions, power conditions, etc., regarding this process. As we have already discussed, as the electron beam impinges the workpiece, the kinetic energy of the electron beam gets converted into thermal energy, resulting in melting and evaporation of the work material. Thus, basically it is a thermal based process, unlike the solid state processes in which the mechanical energy is being converted and used for softening into the material, and then the joining was done. But here essentially this is a thermal process in which the softening of the material takes place because of the heating of the electron beam. Let us see the principle. In general, electron beam welding process is carried out in vacuum. In this process, electrons are emitted from a heated filament called cathode, that we have already discussed how electron beam is generated in a setup. These electrons are accelerated towards the anode by applying high potential difference, which is similar to that of what we use in electron beam machining process. The high potential difference is in the range of 30 to 175 kilovolt between the anode and the cathode. The higher the potential difference, the higher would be the acceleration of the electrons. The electrons get the speed in the range of 50,000 to 2 lakhs kilometer per second. The electron beam is focused by means of an electromagnetic lens system. This also we have already discussed, how the lens is placed on the way or on the path of this electron beam, so that the beam can be converged and focused at a point of our interest, where the two surfaces to be joined or the two objects to be joined are placed. So, this is a critical component, how to focus the beam actually at the point of joining. When this high kinetic energy electron beam strikes on the workpiece, high heat is generated on the workpiece, resulting in the melting of the work material. The molten metal fills the gap between the parts to be joined, and subsequently it gets solidified and forms the weld joint. A schematic is shown in this particular figure, which is in the screen. So, here as I have indicated already, so this is the cathode from which the electron beam will be coming out. This is the grid actually. So, this will be again connected to another voltage or potential difference with respect to the cathode, and this is the accelerating voltage that we can say this is the anode, is connected to the positive end of the power supply, as we can see here power supply. This will be in the range of 35 to 175 kilovolt, whereas this grid voltage will be maintained at a lower value, which will be kept again negative with respect to the cathode, and this resultant electron beam coming out through this, which is being accelerated towards this, will be controlled or focused rather by this focusing mechanism. These are the magnetic lenses or magnetic deflection coil etc., are used to focus this beam onto the work surface, where we can keep the two pieces to be joined here. So, here the penetration of the beam is being shown, as well as the scattering of the beam, possible scattering of the beam is also shown. So, this can give rise to some sort of heating effect or heat affected zone very near to the point of interest or where the joint is to be made. So, therefore, this is another process where we can expect little bit of heat affected zone, because it is basically a thermal based process. However, this can be minimized with proper control of this field or these parameters and this distance as well. This distance is also very important distance, that is the focal distance, where we will keep the workpiece with respect to the beam setup. These are few important considerations here, and of course, as a whole this entire arrangement should be in a vacuum environment. The here major equipment required consist of the electron gun, power supply unit, the vacuum chamber, then workpiece handling device, etc. Let us look into the electron gun assembly. The main function is to generate, accelerate and align the electron beam in the required direction and spots onto the workpiece. This gun could be of two types, one is self accelerated type and other one is work accelerated type. The work accelerated type gun accelerates the electrons by providing potential difference between the workpiece and the cathode, whereas in the self accelerated gun electrons are accelerated by applying potential difference between the cathode and the anode. The anode and the cathode are enclosed within the gun itself. Therefore, the construction of the gun is very critical. It is highly compact also, and it needs lot of mechanisms like cooling as well as insulating the anodes and the cathodes, etc. Therefore, the construction of the gun is complicated here and complex as well. The control of electron density is better in this type of electron gun. It has the following parts like the emitter or the filament, which will be responsible for emitting the electrons, and this emission of electrons will take place because of the direct or indirect heating of the cathode, which is usually done by applying potential difference. Then let us look at the anode. It is a positively charged element near the cathode, across which a high voltage is applied to accelerate the electrons. The potential difference for high voltage equipment ranges from 70 to 150 kilovolt, and for low voltage equipment the range is between 15 to 30 kilovolt. Now, let us talk about the grid cup, which we have seen already in the figure we have displayed. There is a small grid near to the cathode, and which we have seen that the grid was kept at relatively negative voltage with respect to the cathode. There was a separate supply for that power supply connected to that grid, which is always maintained the negative voltage with respect to the cathode itself, of course, because we know cathode itself is a is connected to the negative terminal of the power source. However, grid should be again negative with respect to the cathode. So, here is a difference between the grid and the cathode, and the main function of this grid is it controls the beam. The next unit is electron focusing unit. The unit has basically two parts: electron focusing lens system and the deflection coil. The electron focusing lens system focuses the beam into the work area. The focusing of the electrons can be carried out by deflection of the beams. The electromagnetic lens system contains a coil encased in iron. As the electrons enter into the magnetic field, the electron beam is rotated and refracted into a convergent beam. The extent of spread of the beam can be controlled by controlling the amount of DC voltage applied across the deflection plates. So, this control voltage is very important as far as the controlling of the deflection of the beam is concerned. Now, let us look at the electron gun power supply. It consists of mainly the high voltage DC power supply source, emitter power supply source, electromagnetic lens system and deflection coil source. In the high voltage DC power supply source, the required load varies from 3 to 100 kilowatt. It provides power supply for acceleration of the electrons. The potential difference for high voltage equipment ranges from 70 to 150 kilovolt, and for low voltage equipment 15 to 30 kilovolt. However, the current level ranges from 50 to 1000 milliampere. In emitter power supply, on the other hand, AC or DC current is required to heat the filament for emission of electrons. Also, we have indicated earlier, the electrons are emitted because of the heating of the cathode, which is being done by either AC supply or DC supply. However, DC current is preferred always, as it affects the direction of the beam. The amount of current depends upon the diameter and the type of the filament. The current and voltage varies from 25 to 70 ampere and 5 to 30 volts respectively. The power to the electromagnetic lens and deflection coil is supplied through a solid state device. Now, let us look at another important subsystem of this entire electron beam welding system, that is vacuum chamber. As we have already indicated, the entire electron beam welding process should be carried out inside the vacuum chamber. In this vacuum chamber, low pressure is created by a vacuum pump, which consists of a roughing mechanical pump or a diffusion pump. The pressure ranges from 100 kilopascal for open atmosphere and then 0.13 to 13 Pascal for partial vacuum, and then 0.13 to 133 megapascal for hard vacuum. As the extent of vacuum increases, the scattering of the electrons in the beam also increases. It causes increase in penetration. Now, let us look at the workpiece handling device. Quality and precision of the weld profile depends upon the accuracy of the movement of the workpiece. There is also provision for the movement of the workpiece to control the welding speed. The movements of the workpiece are easily adaptable through computer numerical control. Now, let us look at the advantages of this process. In this process, high penetration to width can be obtained, which is not possible with other welding processes. Then high welding speed can be obtained. Material of the high melting point temperature, high melting point materials like columbium, tungsten, etc., can be welded very easily by this process, because we can obtain very high temperature by this electron beam. Then superior weld quality is obtained due to the welding in vacuum. This is another important aspect, where the in process oxidation possibility is reduced because of the vacuum we use. And then of course, the effect of atmospheric nitrogen also gets reduced because of the shielded environment. Then high precision of the welding is obtainable. It is a very precision process. Distortion is less, highly focused. That is why the distortion, nearby distortion is very less, or the weld distortion is also less. Then the heat affected zone is very minimum. Although it is a thermal based process, there will be some heat affected zone, as we have already indicated. However, how minimal this heat affected zone we can keep, that is where another performance criteria of this process, means this can be restricted to a very minimal zone. And in many cases, difficult to assess points, like some points needs to be assessed through a very small restriction, which is very difficult to reach through some conventional welding rod, etc., can be welded, as this beam, electron beam, can be focused through a very narrow slit. Another important advantage of this process is dissimilar materials. For example, invar and stainless steel can be welded, which are otherwise difficult to weld. Then equipment cost is high, but operating cost is low. Cleaning cost is almost negligible, it is a clean process. Then reactive materials like beryllium, titanium, etc., can also be welded very easily. Very wide range of sheet thicknesses can be joined, like it may be as low as 0.25 millimeter, and then as high as 100 millimeter thick plates can also be welded, which is quite significant. Let us note quickly the applications of this electron beam welding process as well. This process is mostly used in joining refractive materials like columbium, tungsten, ceramics, etc., which are used in basically in missiles. In space shuttle applications, wherein reactive materials like beryllium, zirconium, titanium, etc., are used. This electron beam welding process is used in high precision welding for electronic components, nuclear fuel elements, special alloy jet engine components, and pressure vessels for rocket plants. It is particularly useful in joining dissimilar materials. Now, let us move on to another thermal based welding process, but it is a precision welding process, and this is also considered as one of the advanced welding processes. This is plasma arc welding process. In short, it is known as PAW process. This is again a fusion welding process, wherein the coalescence is produced by heating the work with a constricted arc established between a non-consumable tungsten electrode and workpiece, or between a non-consumable electrode and a constricted nozzle. Therefore, this is significant in that. So, here electrode is non-consumable, that means tungsten electrode we can keep on using for a longer period of time. The sealing of the weld pool is obtained by the hot ionized gas produced by passing inert gas through the arc and constricted nozzle. Filler material may or may not be applied in this process. Let us see the principles of operation of this process, PAW process. In this, workpiece is cleaned and edge preparation is needed. An arc is established between a non-consumable tungsten electrode and the workpiece, or between a non-consumable electrode and a constricted nozzle, which is a prerequisite, we can say. The arc is to be produced and then heat will be produced as a consequence of this arc. An inert gas is passed through the inner orifice. In fact, this inert gas will be responsible for producing the arc. The inert gas surrounds the tungsten electrode, and subsequently the gas is ionized and conducts electricity. This state of ionized gas is nothing but the plasma, what we call normally as plasma. The plasma arc is allowed to pass through the constricted nozzle, causing high energy and current density. Subsequently, high concentrated heat is generated, and with very high temperature is also generated, which is capable of melting any known material. That means, the temperature range is very high. The low flow rate, which is in the order of 0.25 to 5 liter per minute of the orifice gas, is maintained, as excessive gas flow rate may cause turbulence in the weld pool. Therefore, it should be precisely controlled within an allowable rate only range. However, the orifice gas at this flow rate is insufficient to seal the weld pool effectively. Therefore, an inert gas at higher flow rate, which is in the range of 10 to 30 liter per minute, is required to pass through the outer gas nozzle surrounding the inner gas nozzle to protect the weld pool. Now, let us see the plasma arc types, welding types. There are generally two types that is being employed. One is called non-transferred plasma arc welding process, and the other one is transferred arc welding process. In non-transferred plasma arc welding process, the arc is established between the electrode and the nozzle, whereas in the transferred arc welding process, the arc is established between the electrode and the workpiece. That means, workpiece itself is considered as one of the supply ends. So, these are the schematics of these two transferred and non-transferred arc welding system. On the screen we can see. So, this is the transferred arc. Here the workpiece is one of the ends between which the arc is being generated. This is the cathode and this is the arc is being produced. Whereas, in case of non-transferred, so arc is between the nozzle and the electrode, and this is being this is being directed to the workpiece. If we look at the differences between these two processes, then in transferred plasma arc welding process, arc is established between the electrode and the workpiece, whereas in non-transferred, arc is established between the electrode and the nozzle. This we have seen in the schematic also, just now we have seen. In transferred arc system, the workpiece is part of the electrical current and heat is obtained from the anode spot and the plasma jet, while in case of non-transferred arc, the workpiece is not part of the electrical circuit and the heat is obtained from the plasma jet. In transferred arc, higher amount of energy is transferred to the work, since it is directly workpiece is also a part of the circuit. However, in case of non-transferred arc, energy transferred is less, as the workpiece is not part of the circuit. Therefore, the transferred arc system is basically preferred in case of welding applications, while non-transferred arc system is basically preferred in cutting applications. In transferred arc, high penetration can be obtained and therefore, thicker sheets can be welded, and it gives higher processing efficiency as well, whereas in non-transferred arc, high penetration cannot be obtained. It is relatively less than that of transferred arc system. There are different sections within the torch in which this arc is generated. We can see the a schematic of this torch in which this plasma arc is generated. So, there are the construction of this torch is highly complicated. Again, this houses cooling system as well as power supply systems, then gas supply system. The nozzle and the tungsten electrode and cable openings are also being placed here. So, this in the screen we can see the torch, the convention one typical plasma arc torch in which we can see. So, this is the inlet system for the cooling system. This goes like this outlet. So, here inside the electrode, this is the tungsten electrode, this we can see tungsten electrode, which will be responsible for producing the arc basically, and this is the shielded cup, outer shielded cup. This seals the entire arc as well as the electrical power supply system as well. This is the orifice body, this is the orifice gas inlet through which this orifice gas comes inside, and this is the inlet for sealing gas. This is the inlet, and coolant inlet is inside this. And this power supply is connected to this as well as this. This is to anode and this is to the cathode. So, there are 3 connections we can see, one is for gas, one is for coolant and other is for the electric power supply. Similarly, all these 3 are there at this end. So, this consists of the torch system through which, through this end we can expect the arc to come out. These are some typical steps of operation in plasma arc welding process. First of all, the job needs to be cleaned, then the edges to be prepared, the edges of the surfaces to be joined, to be prepared, cleaned and made parallel, then holding the workpiece in the fixture, then we should set up the welding parameters. Then initiation of the arc is important and it is little slightly different also in this particular case. In this process the arc cannot be initiated by touching the workpiece, as the electrode is recessed in the inner constricted nozzle that we have seen in the previous figure. The electrode is inside that and therefore, this cannot be touched and the arc can be produced, as in the case of conventional arc welding processes, where generally the workpiece is touched by the electrode and the arc is initiated and then it is detached and the arc is continued. However, in this case it is not possible because electrode is quite inside and therefore, a low current pilot arc is established in the constricted inner nozzle and the electrode, which will be responsible for producing the or initiation of the arc. Once it initiated, it will sustain. The pilot arc is generally initiated by the use of high frequency AC or high voltage DC pulse superimposed on the main welding current. It causes the ionization of the orifice gas and high temperature, which contributes to easy initiation of the main arc between the electrode and the workpiece. After the initiation of the main arc, the pilot arc may be extinguished. The filler material can be added as in the TIG welding process. Next, we have to move the welding torch manually or automatically in the direction of welding. There are 2 types of techniques involved in this process. One is keyhole technique and the other one is non-keyhole technique. In the keyhole technique, due to constricted arc, high temperature and high gas flow, small weld pull with high penetration, which can be up to 100% of the width, can be obtained. This results in complete melting of the base material beneath the arc. As the arc moves forward, the material is melted and fills the hole produced due to the arc force. The keyhole should be filled appropriately in the end of the welding. Then the power supply and the gas flow are turned off. After cooling, cleaning of the workpiece may be needed. Now, let us look at the equipment and the consumables required in this process. The main equipments are power source, the plasma torch, filler material, the shielding gauge. The power source is a conventional DC current power supply source. with drooping VI characteristics, current voltage characteristics. Both rectifier or generator type of power source may be used. However, rectifier type power source is preferred. The general range of the open circuit voltage and current is like 60 to 80 volt and 50 to 300 amperes respectively. Then the plasma torch is consists of non-consumable tungsten electrode, as we have already indicated. The inner nozzle will be there, which is constricting nozzle, and outer gas nozzle will be there. Then the torch is water cooled to avoid heating of the nozzle, although the cathode heating is required, but the nozzle should be cooled. It is also of two types, transferred arc and non-transferred arc torch, that we have already discussed. Then about the filler material and shielding gases. Filler material used in this process is the same as that used in the TIG and MIG welding processes. The selection of the gases depend upon the material to be welded. The orifice gas must be inert gas to avoid the contamination of the electrode material. Active gas can be used for shielding, provided it does not affect the weld quality. In general, the orifice gas is the same as the shielding gas. Now, let us quickly look at the applications of this process, plasma arc welding process. This process is comparatively new process and is therefore not yet very popular as that of the other established processes. However, one can expect that this process will come up in the popular category very soon. This process can be used to join all the materials that can be welded by the TIG process. Therefore, the versatility we can see is very high. Piping and tubing of stainless steel and titanium can be welded. Then submarine and aeronautical industry and jet engine manufacturing industry, this is used. Then for welding of electronic components also, this process is used, quite widely used. Now, let us note the advantages of this process. In this process, welding speed is quite high, penetration is quite more, and higher arc stability can be obtained. The distance between the torch and the workpiece does not affect the heat concentration on the work up to a considerable or reasonable extent. Then addition of the filler material is easier than that of the TIG welding process. Then thicker job can be welded and higher depth to width ratio can be obtained, resulting in less distortion. Let us not forget to note the disadvantages of this process as well. This creates higher radiations as the plasma is involved, which can be a deteriorating point as far as the human health is concerned. Then the noise during the welding, that is also a concern as far as the operator's health is involved. Process is complicated and requires skilled manpower. Then the gas consumption is high. Here this shielding gas is required. Then higher open circuit voltage is required, which necessitates higher safety measures. Now, in the end, let us summarize what we have discussed today. In this particular session, we have discussed two important advanced welding processes, metal joining processes, that is of both are thermal in nature. One is electron beam welding process, the other one is plasma arc welding process. We have discussed the principles of operations of these two processes. We have discussed the main components involved in these two processes, and then their applications also we have discussed. We hope this session was interesting and informative. Thank you.